Hey everyone, Black Box Engineering here. So, it's been a while since I've done a technical video. Yeah, I don't want to abandon that because that's something that I'm also passionate about. Again, this channel has a lot of different focuses, and I don't want it to just be games and commentary. I also like a lot of technical stuff. Something I've explained before, but just want to make it clear that I have a lot of different areas of interest here. So, today I'm going to be talking about something in electronics that throws people off pretty easily. There's technically a lot to cover with it because it's not just as simple as one thing, because there's multiple different contexts that can apply. So I won't get into the nitty-gritty details too much. It just kind of goes over the basics. So let me start off where the idea is presented when you start learning electronics, especially when you're doing analysis for writing equations. Well, many of the things that you write for equation purposes, professors usually tell you to assume some kind of polarity. All that really is supposed to mean is like assume like a plus or minus on one side or the other. Really, it just, all it means in terms of how equations are written, it usually depends on what you quote unquote meet first when you follow like a loop. I can switch to LT Spice just as an example here. Give me a second. So let me just switch to LT Spice because this is the only way I can show you right now. Alright, so this is, I'll just do a one resistor example because that's just super easy to do. So let's just assume like a 5-volt power supply, and then just add a simple resistor, and I suppose just kind of leave it blank. Just imagine that there's no value attached to it. You just leave it as R1, and then this is just as an example for writing an equation. So anyways, the normal context, assuming that you go clockwise, and people usually do go and end up going clockwise, that's a typical direction for doing a loop. The equation would, let's say that we start at the lower left hand corner, it would be -5 because we see a negative voltage first, and it's 5 volts, so we'll just call it -5, or you could just leave it as -V1. Let's say if we didn't know what this was, it would be -V1, and then we've got nothing. Keep following the loop here until we meet a resistor. Since for the sake of, like, let's say if you're learning from scratch, right? You don't know what the way that the current is supposed to go, even though most people just assume this way. But let's say that you didn't know if it went this way or this way. So professors usually just tell you to assume like this. They just say, well, just assume that the top is positive and the bottom is negative. We can change that if we come across that in a different spot. So the full equation would be negative V1. We come across and meet our first quote-unquote sign plus R1, and then since we do a complete loop, it would equal 0. So that's like the Kirchhoff's voltage law version of what this is. And of course you can substitute values. Oh, sorry, I forgot to label the current. It would be I times R to get the voltage. So we can just label it, I don't know, A, I guess. Current A is flowing through this. So, yes, this is how most people would write an equation. And I have to explain that this is just for the purposes of writing an actual equation. The concept of polarity gets actually kind of complicated because not all parts are polar in real life. This is kind of another one of those disconnects between learning and the physical world. So what many people think is, well, that must mean that every single component must have some kind of polarity. So people get really confused on how to write equations because, well, like if you were to use like a switch or some kind of active part like a transistor or stuff, it can be really hard to know to use plus or minus because you've been told about this concept of polarity and you have no idea. And the problem is it's just presented as a basic equation kind of thing. But in the real world, parts do and don't have polarity depending on the design. So passive parts, such as resistors, certain capacitors, and inductors, anything that doesn't require an external power source to make it work, like transistors for example, those by default aren't polarized. Now I said some capacitors aren't polarized, so this would be like a AC cap with no polarity symbol on one side or the other. These are generally non-polarized, so they can conduct either way, going from here to here or from top to bottom. That's because they're usually used in AC signals. With AC, now if this was a polarized capacitor, dang it, I always forget where it's at. So it would look something more like this, where this is your positive voltage and then this is your negative voltage side. These kinds of capacitors are usually used in DC situations. So this is very important because these kinds of capacitors, if you were to hook it up the other way around to a positive supply, you would actually blow up this capacitor if you tried to hook it up this way. So in this particular context, polarity matters for this specific kind of part. Meaning one side is going to be a positive charge and the other is supposed to be a negative charge. Anything that a power source, for example, is always going to be polarized or positive and negative. So yeah, polarity in that context is the direction of current flow. Diodes are polarized, for example. The quote-unquote positive side of a diode is typically the large square, the large flat triangle side, and this is just for a basic diode, and this would be the negative side, where current would flow from top to bottom, not the other way around. If you were to rotate this around, current would not flow this way. It wouldn't blow up, it would just not ever flow this way. So you basically would have an open circuit from here to here if you were to connect wires. So in that instance, a diode acts as a one-way like path in many like applications. So these kinds of of diodes are quote-unquote polarized because they only conduct in a certain direction. Again, it always depends on the type of part. So then a different kind of problem appears in the context of an inductor. Inductors are not polarized. They will work the same way regardless of how you orient the part. Even if you were to turn it upside down, it's still going to kick back the voltage the other way. So in that instant, in this particular context, it's not driving anything, meaning that the magnetic field is not interacting with anything. In terms of current, it will go this way or this way. It does not care because of how an inductor, all it really is a coiled piece of wire around a piece of ferrite. So wire does not have polarity. It goes forward or backwards, forward or backwards. So you could hook this up going from top to bottom, and once you turn off power, let's say you had a switch here, like let's say that we cut the line, let's say we let this charge up, and then we have a magnetic field around this inductor, and then we cut this, and then all of a sudden that magnetic field would have to collapse in on itself, so where the energy has to go somewhere. So once that magnetic field collapses, the only way for it, since we charged it this way, the only way that it can go is the opposite way, going up and through the resistor. So it doesn't matter if it's upside down. Okay, so now we see that the coil is going counterclockwise. If you were to imagine this as a 3D thing, it still doesn't matter if it goes clockwise or counterclockwise. It doesn't matter, only because it's still going to generate a magnetic field. It might go the opposite direction, where the North Pole in this instance would be on the lower part of the North Pole. Let me just draw it. The North Pole would be down here in this instance because of the way the current is flowing. Sorry, let me just draw back the wire here. So current is flowing down counterclockwise, going this way. The North Pole would form at the lower part of the inductor, and the South Pole would form at the upper part of the inductor. It doesn't matter if the field collapses, because the current is still going from positive to negative, going down this way, because let's just say that we're assuming that, and it usually does, because this is the lower potential. It's still acting as a quote-unquote resistor in that way. So current is going up and down through this from south, or let's say that there isn't a magnet pole at the moment. It's still going from here through the thing counterclockwise, generating a magnetic field from north to south, north to south. The collapse of the magnetic pole doesn't matter if north is at the top and south is at the bottom, or the other way around like this. Again, when current was going this way, it can't kick back in the same direction. It's just not how inductors work, because like in a physics sense, it has to kick back the other way, even regardless of how the magnetic field collapses. So it can't go the same direction as what the current was flowing. It simply can't, because of how equal and opposite reactions work. If current was going down through the thing like this, just because the magnetic field disappears doesn't mean that it's suddenly going to grow stronger and just shoot like the opposite way, down and up through the resistor this way. It can't do that, regardless. I know I'm kind of beating a dead horse here, but the physics don't allow it for current to just get stronger the same direction. It has to be the same strength going opposite, regardless of which way the magnetic pole is oriented. So that means that current has to shoot back going this way when the power is removed. That's something that took me a while to figure out, because someone brought it up in my practical experience on a day-to-day basis when I'm working. This came up and I had to explain this because it's kind of hard to understand that regardless of the travel and current, even if the north and south poles switch, it has to kick back the other way. But anyway, okay, so yeah, it might seem counterintuitive to think that a different north and south pole would make it still go the opposite direction, because you were thinking that, well, north being at the top versus north being at the bottom is such a different position. But the thing is, current is still flowing from top to bottom. It's still going in this general same direction, regardless of the way that the inductor turns. So in that aspect, it's still traveling down. It just turns different, whether it goes this way or the other way. That's why people get really confused about inductors, because the magnetism that they generate is quote unquote polarized, but not in the same way that electricity is polarized. Electrons are still flowing from, well, conventionally they're flowing from positive to negative. In reality, they're going from negative to positive, but regardless of that, let's say, just for convention's sake, electrons are still traveling down. They cannot, when that magnetic field builds up and there's a loss of power, it's going to reach saturation. That magnetic field strength has to go somewhere, and it cannot push current in the same direction that it was going. It has to go in the opposite direction, regardless of orientation. I'm just trying to explain it as clearly as I can explain it. Again, it's not super intuitive, because you would think that north and south would matter, but it doesn't. So you might ask, well, why do DC relays have like plus and minus? It's not that the inductors that control the relays have polarity. That's not really what's going on. In fact, the relay itself is depending on the orientation of the magnetic pole. So let's just get rid of some stuff here. Okay, so just give me a second here. That's not very visible. Okay, I'll cut that part out. So let's just say that this was a relay. I just drew a box around here to kind of indicate that let's say that this was a switch controlled by this coil. So, like I said, some people might ask, well, why are relays often drawn with the plus and minus then, if the coil technically isn't polarized? So that's a really good question, and I can answer that. Just give me a second. So typically you would see little markings on a DC relay saying, hey, we want you to power the relay from top to bottom, or whatever the pin direction is. Positive. There's a definite positive, negative. It would still conduct if you were to apply power the other way, but like I said, a magnetic pole is now generated. My point is, there would be these invisible lines curving this way out and from north to south. These are the magnetic field lines, like a curve from there to there, and they get weaker as you get bigger and bigger. Anyway, the North Pole would form at the top and the South Pole would form here. Like I said before, this is probably not a very good example. I kind of drew the switch in a upside down way. Let's redo that a little bit here. Whoops. Okay, that's a little bit better. So, anyway, this switch material, this sticking out red line, is ferrous, meaning it has a little bit of iron in it. That's sensitive to magnetic field, and the quote-unquote North Pole, wherever the break lies, I would imagine that somewhere halfway the material would be magnetically polarized in one way or the other. Remember that north is attracted to south, so the South Pole would be kind of up here, and then the North Pole would be down here. Let's just write that. So remember, this is the North Pole of the relay, and this is the South Pole of the coil, I should say. And let's say that the switch, it would have to be the other way around. So right, so the ferrous material in the switch body or contact or whatever you want to call it would have to have some kind of polarization splits at some point. So you need the North Pole to form so that the South Pole is attracted to the North Pole. Again, this is specifically for DC relays. If you were to put the current the other way, remember that the North Pole and South Pole switch, and south repels south and north repels north, so it would not close. So that's why DC relays require some amount of polarization. Now, there are some relays where it doesn't really matter which way you go. They've got special coils where the magnetic poles are generated in such a way that this is still attracted to this. I'm not sure how the coiling works, or maybe it's like a half and half kind of thing, where it's like coiled one way coil the other way. Maybe it evens out so that north and south still applies regardless of which way you do this. It also could be possible that the north and south here are in a way where it's such a small amount that regardless of where it's at, they're going to be relatively close together, kind of at one point, so that it just snaps closed regardless of which way you go. And AC relays, they don't care which way you plug in the coil, because the north and south pole is still going to be generated in a very particular, they're going to kind of technically flip-flop, or they go south north south north south north, but this is still going to pretty much stay consistent. So again, there's something special with AC relays where it just kind of snaps into place. It might be the strength of the magnetic force over here is stronger than this, so it just snaps it closed. So regardless of it, if it's going like up and down, up and down, up and down at 60 cycles per sec, or 60 hertz. So yeah, that's where it gets a little funky with relays. It's not the electrons that are polarized, or not electrons, the direction of the current will still go either way, because it's not a quote-unquote polarized part, but the magnetic field is polarized. So that's the difference there. There's other more complex parts. Active parts meaning things that require external power, like transistors, other kinds of power supplies. Certain digital things have to be polarized, meaning again they require a definite direction of current. But it all depends on what kind of part you're talking about. Pretty much all active parts are going to be polarized. That's just the nature of it, really. So anyway, I hope this kind of introduction helped you a little bit, helped you understand it a little bit here. Polarization can get kind of complicated, especially with more advanced parts. Some things have negative voltage generation, and that's a whole different kind of application. Some things require negative voltage references for power, such as like op amps and stuff, because op amps require a differential, and that's why you usually see operational amplifiers have a plus V and a negative V to get you a differential on the input, meaning an exact positive reference and an exact negative reference. And negative voltage generation gets very tricky on how that's accomplished. It's a whole different kind of polarization. You're basically reversing positive and negative to where you're forcing the negative to be on the other side. It's very complicated, but yeah. So in terms of like electricity and flow, polarization always means you expect it to flow from one side to the other, but not the other way. It's pretty much limited to positive, negative. That's completely different from analyzing, where you assume plus and negative for the purposes of an equation, but it doesn't mean the part itself is going to behave that way. It's just for calculation purposes. So I'm going to edit out some of that repeated stuff. Like, comment, subscribe, and remember, think outside the box and stay wise. See ya.